This is not a talk intended for a Mojo compiler engineer necessarily, and this isn't a tutorial on how the compiler works, but it's more focused on how the language works, intended for users, intended for people who are interested in the machinery of how a language like this works together. Also, this is the first talk. This won't go into the deep how Lifetime's machinery works and how to do advanced features. That'll be for next time. So today we'll start with what is ownership in the first place, and then we'll go through 3 different levels of how ownership gets handled in Mojo and what it means, starting with the type checker. Define terms. What is ownership? Well, we have these things called values. Values float around in a program. Somebody, somewhere, something has to decide who destroys the object, when does it get initialized, can there be holes in its lifetime, for example? When do you get copies? Some languages have garbage collectors, for example. As you know, Mojo doesn't want to have a garbage collector. And so we need to have a bunch of machinery across the compiler that works together to actually make sure things get destroyed. We also have to decide, when does something get copied? That's actually a really important thing for reasons we'll talk about later. All these things kind of work together. All these subsystems have to compose in a nice way and work together so that you get a coherent user model and you get things that people can understand. When we tackle this in Mojo, what do we want? We want a safe model. This means that if you use Mojo in a reasonable way, you get memory safety, you get predictability. We also want this to be helpful. Let me pick on C++ here. You define an int on the stack, it defaults to being uninitialized garbage. And then if you go ahead and use it, C++ is very happy to let you go do that and you'll get async problems, right? That's not acceptable for Mojo. But we also want this to be helpful. We want to be able to provide powerful features, particularly for library developers. What the outcome of all this is we need 2 subsystems of the compiler that work together that then provide this. Of course, the first analogy tends to go to Rust. And lots of people love Rust. There's a reasonable question, which is, since Rust has solved this and it has a theoretically simple model, why not just do the Rust model? If you look into Rust and if you squint the right way, it's actually pretty simple what it does. It says that it has these references, it has these things called lifetimes, they're hierarchical in scopes, and they have a couple of simple rules, like you can't have multiple references to a thing and mutate the thing at the same time. So I love that. That's actually a wonderful conceptual model. But it's the conceptual model, like Git is simple if you know how Merkle trees work. It's true from the sense of there's a unifying theory and there's some principles behind it, but then the reality is you have to learn how to use Git. And similarly with Rust, that's the challenge, right? Is that the reality of Rust, when you map theory, is it has lots of weird special cases, inference rules, it has magic behavior, the fact that it implicitly moves, it's explainable, but it makes it surprising to people. It really gets unraveled when you start doing async or things like this. This isn't something that I think we want for Mojo. My opinion and perspective on this is that we want to learn a lot of things from Rust, but we don't want Mojo to be Rust. Before I dive into all this stuff, I thought it'd be good to give a roadmap, a top-level view of how does the Mojo compiler work. Like many compilers, logically, Mojo starts with a lexer and a parser. These are the things that break the source code into tokens, figure out a parse tree, and then it has a type checker. The type checker is responsible for deciding, okay, you have x plus y, what is x, what is y, what is x plus y return? In practice, these are all integrated. And so this part of the compiler is in the Mojo parser directory. There's another important piece that we'll talk about called check lifetimes. This is an MLIR pass. This happens after the parser is done. You can run it from the kgen opt tool as a standalone thing. This is another big piece of the puzzle, which we'll talk about later. There's a bunch of stuff that happens after the front end that we're not going to talk about today. So that's a map of where we're talking about. We're talking about front end things, not optimizations or code gen. So let's zoom into that type checker. What is a type checker for? Again, it's about deciding what the types are for values and generating the IR that comes out of the parser for expressions. But importantly, it's also where implicit copies come from. This is the first step that's really important for building and forming that user model. When we go into this, it's also very important to frame what is Mojo's opinions about types? What does the language enable? And it's actually surprisingly general, surprising to some programmers at least, where it supports types that are not copyable. It supports types that are not movable even. In Rust, that's not really a thing. It supports custom move logic, custom destructors, custom all this kind of stuff. And so it has a very general, very flexible expressivity model. All memory types have identity, which is a really important thing when you get into async propagation and copying and closures. And Mojo also supports non-default address spaces. This is advanced stuff, right? This is what allows Mojo to express things that many people in the industry need in terms of GPU programming, but also atomics, where if you think about an atomic integer, the address of that integer is part of its identity. You don't want that thing to move around. The address is actually important. Being able to define these things is pretty critical for modern hardware. Now, the advanced crazy cases are important, but also it's very common to have simple cases. Mojo provides this register passable thing for things that don't need memory identity. It provides the value decorator so that you can synthesize simple cases and get all the copy constructors and stuff that you want. But starting from this generality piece is really important because it shapes how the type checker has to work, shapes how lifetime management, ownership management has to work. It's cool to support specializations, but given a general model, you can specialize. You have to solve for the general case. Today, we're going to be talking about the general model, even though we like most people using aggregations of simple value types, for example. So how does a type checker work? Well, like many type checkers, not all, but like many type checkers, C++, for example, it's context insensitive. This is actually a very powerful thing when you care about things like compile time. My experience with Swift is we tried to make really fancy bidirectional Hindley-Mindler type checkers and things like this, and it's really great because you can have very beautiful minimal syntax. But the problem is that compile times are really bad, particularly if you have complicated expressions. And second, the error messages are awful because now you have global constraint systems, and when something goes wrong, you have to infer what happens. And to the user, they can't know that something over there made it so something over here can't type check. In my experience, it sounds great, but it doesn't work super well. Also, I'll say that for all the different damage and problems that C++ has, the type checker seems to work. In the case just like that with Mojo, what happens is you take an expression tree that comes out of the parser. That's a different talk. When you say I have Y and I have Z, how do I type check Y times Z? I go look at the type of Y and Z, I do whatever I'm going to do, and then I emit IR. Mojo is pretty unusual as far as compilers go in that it doesn't generate a type checked AST. In fact, it doesn't really generate an AST in a traditional sense. And so it uses MLIR for the representation of all the stuff, including the types, which is unusual. But the output of this is that you have to decide, how am I going to model this? What am I going to think about? Each type check operation has to be context insensitive. And so it doesn't know the global scope of what's going on in the program, doesn't know about other statements. It's really thinking about an expression at a time. And so actually what happens when you type check is you generate some IR. For example, with star, you say, okay, I'm going to generate a call to mul. Mul will return some MLIR value, but then I'll also return a value classification. And there's three kinds in Mojo. There's RValues, LValues, and BValues. And so I'll talk about what that means. There's tons of interesting things in Mojo I'm not going to talk about. This is really taking a very narrow slice of all the cool things and just focusing on ownership, of course. Let's start with Mojo talking like a pirate with RValues. So what is an RValue? As with C++, an RValue means you have an owned reference. So this is something that you call a function, it returns a string. If you're returning a string by value, the caller gets a string back. And so typically the function result for a function call ends up being an owned result. And then what that means is that you can then pass that into things that take owned values without a copy.
I'm just going to clarify a few terms there for people that aren't familiar with Mojo. In Rust, all the arguments take ownership by default, which means the value has to either move or copy into the function. But in Mojo, all the arguments are borrowed by default, so you have to use this owned keyword to get that behavior. Now, the term that often confuses people is an RValue. That comes from C, and you can think of it as the right-hand side of the expression. So in this Rust example, it's transferring ownership of that into this function. Now, I can no longer use that because I've moved the RValue into take. If I were to clone it, then it's moved a copy in there. So I can still use the original S. And the same concept applies to Mojo, but you have to use this caret operator if you want to get the same behavior. So now I can no longer use S because it's moved into take. But if I remove that, then it will do the optimal behavior. So it will still move if I don't reuse it. But then if I do reuse it, then it will do a copy. This is all about making things as simple as possible for people where they don't get hit by the borrow checker. But if they want to optimize things and make sure that they're not doing any clones, then they can explicitly use this caret operator. Anyway, back to Chris.
There's a goofy language struct, and it has a name argument that it takes. It wants to take ownership of that string that you pass in. If you construct a new string, either with a string literal Python or a concatenation of plus of Mojo and Fire, this is an expression, plus returns an owned string. You can pass it directly into this initializer, and there's no copy made because this thing returns an RValue. When you think about ownership, when you think about creating and passing around values, owning a value is really great because it means you have that thing uniquely. And with unique ownership, that means you don't have to worry about destroying it and copying it and things like that. This, I think, is hopefully familiar if you've used C++. RValues are very common in multiple different languages. Next thing, LValues. It's a thing that can be mutated.
The new keyword that you won't be familiar with if you haven't used Mojo or Swift before is in-out. This means that it's transferring ownership in and then returning it back out. This is similar to a mutable reference, but it has a couple of important differences. Functionally right now, this Mojo, Rust, and Python program are all the same. They're all updating the R value here. But in Mojo, I can also update the L value, so I can rebind V to a new list. And you can see it's reflected on the caller side. In Python, you can't do this at all. So if I tried to rebind that to something new, it would no longer work. You can see that this L value still remains the same even after it's mutated in this function. Sometimes people will call this some types are immutable, like a string you can't modify. So if I said hello and I tried to update that to world, people might expect that this would update the outer scope as well, but nothing happens. It's still hello. And one other important difference about in-out is that you can subscript as well. If I pass in just the first element and then make this an int, then I can modify it and it still works as expected. So those are the two important differences for in-out.
Notably, the thing that you're mutating, you don't have ownership of necessarily. It's conceptually a thing in memory. This is either I have a local variable on the stack. So I have X. X can be mutated. I can assign to it. I can increment it. Incrementing is just passing it in out, by the way. I can have a function that takes values as in out, and so I can modify them. L values, I think, are also quite familiar. This is like passing a mutable reference in C++. And so that allows you to read from, write to, all good, pretty simple. Eventually in Mojo, we'll prevent aliasing with other references. And so we'll build that in the future. But this L-value concept is hopefully pretty simple. Now, when you think about the type checker, going back to expression trees, this notion of what is an L-value is something that cascades through the evaluation. If you think about, I have X, which is a mutable L value. When I get access to the field is also mutable. And if I can assign to X, I can also assign to a subfield. The way this works is when you're type checking X.field, is you say, if the left-hand side's an L value and the right-hand side's a field that's stored, then I can compute the address of the field and then return it as a mutable thing. And so all of these things end up composing. I'll point out two interesting things, which is that owned arguments that we were just talking about, they take an R value on the caller side because per the previous slide, you want to be able to pass in an owned value and you're taking ownership of that thing from the caller. That's what owned means. But we actually allow you to mutate an owned value on the callee side. And so in this case, even though B is owned, I can now go mutate it, I can do something, and that's because it's mine. I have it and I can track the lifetime, and we talk about how that works. But for owned values, because you own them with the argument convention owned, it means you get a mutable thing. And so owned values are actually L values for a function argument. I'll also say, again, for sake of generality, L values can be computed. So there's this get item, set item thing, and all that kind of stuff. Mojo supports that. This is just syntactic sugar, and so this talk doesn't talk about any of this stuff. Now, what about borrowing? Borrowing is when somebody else owns something and you have an immutable reference. So you're saying, I'm going to refer to something somebody else has. They own it. I want to borrow it for a while, right? So they're going to continue to own it. It's there, so I can't go change it, but I can read from it.
The borrowed will be familiar for developers coming from Rust, where you have an immutable reference, or C++, where you have a const reference. But in Mojo, all the arguments are borrowed by default, so you can elide that keyword and you get the same behavior. Borrowed is the best default for performance because it avoids copies, and then if you go and try and modify something, then it will give you a nice compiler error telling you how you need to fix it. So conceptually, for a lot of programmers, all they need to know is that they have to add in-out if they want to modify on the caller side as well. So that covers all ownership keywords in Mojo.
I can also form immutable references to this thing, which we'll talk about references later. The power of a borrowed value, a B value, is that you can get access to things without copying them. Not all languages have borrowed values. Swift, for example, doesn't really have a notion of a borrowed value. What that means is that lots of things have to copy. Swift as a language, for example, does a lot of copies coming out of the type checker because it doesn't have a way to express this correctly. And then it has later compiler passes and other things like that that try to clean up the mess and get rid of extraneous copies. And so the fact that Mojo models this correct way is actually quite powerful because the very predictability allows the compiler to reason about where these copies happen. Now, this isn't rocket science either, right? In C++, we have this as const references. And so I think you've seen similar things like this before. But Again, getting this right is really key. And this also composes into the type checker. Again, the x.field example. If x is a borrowed value, then the sub-reference to the field ends up being an address calculation that returns another borrowed value. These things propagate the right way. In Mojo, I think many people know arguments default to being borrowed. And so what that means is that you can have an owned value like my string on the caller side. You can pass around references to it, and it all kind of composes naturally. How does this all work? These things all intersect. The important thing to think about is we need a very simple set of rules that compose. These three concepts, the borrowed value, the R value, and the L value, now we can look at how do these things work when they intersect. Here's three functions that define one of these things each. So BV is a borrowed argument. The fire string is an R value. It's a new string value I construct. And an L value is an in-out argument. This gives us examples of the three classes of things. So now what happens when we pass these? So if you have a borrowed value and you pass it as a borrowed value, everything's good, right? A borrowed value is logically a const reference. It's a pointer. Just pass it right on. What if I want to pass an R value to borrowed value? Well, I own this thing. That's cool. The caller owns the string. And so I can just pass a reference to it, no problem. You're just going to read it. It's totally fine. You can mutate if you want to, but since you just want to read it, that's also totally fine. What if I want to pass an L value? That's also totally fine. I have a mutable reference. I have a mutable pointer thingy. I'm passing as an immutable. It's a decay, so it's like a little change in type, but it's just passing a pointer around. No big deal. All's good. And from this perspective, borrowed references and mutable references are very friendly. They get along. What about R values? If you need an R value, and this is something that can be surprising to people, if you say I take an owned argument, that doesn't mean I'm taking it away from you. What that means is that the callee gets a value of its own that it can take and go. And so if you have an R value and you're passing it in, this is where you're saying, I've created a thing for you. You can have it. There's no copy. There's no nothing. It's simple and easy, and it's all good. But what happens if you have a borrowed value or an L value is you have to copy. When you think about where do copies happen, this is because somebody needs a thing. They want their exclusive ownership. And so if you're not going to give up exclusive ownership, you have to actually do a copy. Now, why would you want an owned argument? So initializers often take their arguments as owned. Owned allows you to propagate out the call tree the fact that you're going to do a copy. And so if you think about it in C++, for example, you can define your person struct. Your person takes a const string reference as the name, and then it stores it into a local property. That conversion from a const string reference to a stored SC string will do a copy. That's what this is. This is the BValue to RValue conversion that happens within C++. C++ is way more complicated, by the way. By saying, I take an owned argument, what you're doing is you're pushing that copy out to the caller of the initializer. What that means is they may have to do the copy, but they may not. You're allowing the API author to express in a simple way where copies happen and then what kind of types are compatible. Come back to generality, not all types are copyable. This notion of being able to push owned arguments out is not just about performance, it's also about correctness when you care about non-copyable types. Having the ability to express this is really important. But now you get down to the L value, right? So what if I want to pass something in out? This is where you say being able to take a reference to something that's mutable, that the caller is telling the callee they're allowed to change it. If the caller just knows it's a borrowed value, you can't do that. Like you can't take something that you're not supposed to modify and pass it to somebody else to modify. That's not going to happen. Similarly, our decision so far is that you should not take an owned value like a string or something and pass it to somebody who's going to mutate it. This is a policy decision, by the way, but the reason for that is that if you're calling a plus equal method on something that's a string literal, you're going to do some mutation and then throw it away. What we force to do by disallowing this conversion, if you want to be able to call plus equals or something on an R value, then what you do is you define a local var. Say var temp equals my expression, call plus equals on the var. That makes it explicit in your code that you're doing a mutation. And then if you're ignoring it and throwing it away, at least it's clear in your code that you're doing that. And so this is a small bit of protection for Mojo developers. Now, this is something that's been discussed. We could change this policy, but that's the current rationale for that. Now, of course, if you have an L value and you're passing an L value, everything is good. Again, you just have a pointer and you're passing it on. And so this all kind of composes out. This one chart is why you see copies happen and when. And why also you'll see you want to use owned arguments. And when you think about where copies happen and how to work with non-copyable types, all this stuff comes together. This is a chart that could be useful if you refer back to it later.
Is an R value always a literal then?
No, here I'm just trying to use super simple examples, but an R value is very common. It's usually the result of a function. The output of a function call is almost always a owned value. So if you say, I'm going to go create your person object, it returns an owned person or whatever that is. If I call the plus method on string, it takes two arguments as borrowed arguments, and then it returns an owned argument out. So that's the most common place that they come from. So for compiler nerds in the group, you can see this directly in the Mojo source code base. You'll see we have borrowed values, RValues, LValues. Then we also have this matrix across the other dimension, which is, are they a memory type? What you'll see is an MB value, MR value, ML value, or are they a scalar SSA register type, like an integer or floater or a low-level pointer, in which case you get the S version of this. And we also have this P thing for parameters. This allows us to reason about in the compiler the two cases of if it's in memory, it has an address, and if it's not, it has an SSA register. I'm not going to spend a lot of time on this. Let's go back to this thing, right? So isn't it kind of annoying that you have to copy? Like, we don't like copies generally for performance. Also, it means that they don't work with memory-only types. And so how do we wrangle this in the language? Well, a very common pattern is that you build something up and you pass it off, right? Here's kind of a silly example of this, but I have a string name. So this is an L value. Any reference to name ends up being an L value. I'm going to do some stuff to go build up name or change it or do whatever I'm going to do to that string. And then I'm going to pass it to this initializer language. When you're looking at this, it's obvious this is last use of name. But the rules here about how to pass this, the initializer takes the argument as an owned value, right? For the previous chart, that would have to copy. Well, this thing is where this transfer idea comes in. Transfer as an operator, what it does is it takes an L value, which is not owned. It takes a B value, which is not owned, and it produces an R value. And so what transfer does, if you zoom into it, is it's all about giving up ownership of a value that you have to somebody else.
Is this the same as std move in C++?
This is the last thing I'm going to talk about because they bring it up a few times, is this std move. So you can see there's a lot of code here to get the same behavior as what we have with this owned keyword. When you move it in, if you try and reuse it, then you're going to get a seg fault, which is shown down here in the terminal. In Mojo, you get a compiler error telling you that you've transferred ownership, so this is no longer initialized and you can't use it.
It's very related. The use case is very similar. I'll talk about later how it's a little bit different. The major difference is the contract of std move is that the value you're moving out of is still alive. The destructor still runs on that old value. When you define a move initializer in C++, the idea is you like suck the guts out of it, out of the value, but C++ doesn't track lifetimes correctly, or can't, and does not. The way that it ends up working is that you have to put it into an invalid state or a null state or something that the destructor doesn't do anything. This is one of the reasons why C++ is unsafe. I'll talk about later how this works. When you transfer ownership out of name, the destructor doesn't run on name. Right.
So this is a better version of std move with more solid semantics.
Yes, that is a fair way to look at it, yes. For a user, that's how you should think about it, is this is like std move that's way better.
Do we currently have a optimization where if name is not used subsequently after P, it's automatically a transfer?
Hold that thought for like five slides, but the answer is yes. So that's what the transfer operator is. This is a question that I think a lot of people ask. Historically, this got conflated. We had a thing very much like std move called take, and so we just got rid of that and made it a separate thing. And I think it really helped clarify the understanding of what transfer is. But when you see these things, it is, I think, a very reasonable way to think about this is it's like std move. Now, here's a question. So I just spent all this time talking to you about how the type checker is context insensitive. This thing is only safe, right? This will prevent the destructor from running on name. But what if there's a use of name after that statement? Well, the compiler is not supposed to allow that. This is supposed to be a safe language, right? But the type checker can't do anything because it doesn't know about data flow, it doesn't know about other statements or expressions. This is why ownership is a joint responsibility between the type checker, which has these R values and L values, and it has these simple context insensitive rules, and then data flow. After the parser runs, it goes and generates a bunch of things. It then generates a type checked IR. You can output it from MLIR. You can look at the code that it comes up with. It will not have destructor calls in it, notably. After the parser, then there's this new thing called check lifetimes, this standalone MLIR pass, which goes through and it checks to see all the flow sensitive properties. Let's talk about two of those. One is uninitialization. I want to tell you about how references to variables are LValues. A stir is an LValue. In this case, it has no initialization. It starts out uninitialized. It would be an error to read this before you stored it. But for the type checker, it can't know that. It doesn't know how data flows. It's got its big brain focused on add versus add. It can't help with that. But if you look at this example, it actually gets more complicated, right? I have a stir, I initialize it, I use it, then I transfer, like we were just talking about. What if I use after this? Mojo, as a safe language, has to generate an error. It has to generate an error in this case, but not this case. This is clearly a data flow problem. This is also a super simple example of this. It turns out that you need to handle the full generality. Otherwise, people that reasonably expect Mojo to have a big brain will get grumpy because you don't want to complain about invalid things. I have an uninitialized thing on the stack. I have an if. I'm going to assign it. I need to allow this use to us normal humans. This is clearly initialized, and so it's fine to write this. But then if I forget to initialize it on the else branch, well, then it's an error. Right? This is the shape of the problem that check lifetimes has to solve. I'm not going to dive into how it works, but it uses data flow analysis. It's a bit vector analysis. It's actually relatively simple conceptually. What happens is it just make sure that on all passes of the program, a value is initialized before it's used. And when a consume happens, what that does is it transitions from being initialized to being uninitialized.
So when in doubt, do you err on a safe side? Can we run in the situation where a data flow analysis tells you that it's illegal, but actually the error doesn't happen at runtime?
It's 100% sound within the scope of its model. We'll talk about later the dangling pointer problem. We'll talk about references, but for simple local uses like this, it is 100% sound. It's very simple. You can ask Mojo users on the call. You don't get uninitialized error messages that are weird. I haven't seen complaints about that, aside from when things were getting debugged. I think that it is completely sound. But to flip it around, you go malloc an unsafe pointer, the compiler's not tracking what the pointer points to. They'll track to make sure the pointer itself is initialized, but it doesn't refer to the indirect thing. Where did these argument conventions come in? How does an argument convention work for a data flow checker? You can go through them. If I take a borrowed argument, it's an immutable reference and it can't be assigned to. So the parsers are in the type checkers already resolved that. We know that it's structurally correct. All we know is this data flow system is we just say X is valid coming in. It's also valid going out. Easy stuff. There's no problems that can be had here. We know that if you have a borrowed convention, that's totally fine. But if you have in out, with in out, it's also simple, but it's a little bit more complicated because it's mutable. And the invariant is that it's initialized on entry of the function because somebody gave you a live object. It's initialized on exit of the function because you have to return it back. That's the out part of it out. But you can totally go nuts and like transfer it. As long as there's a valid object in it when you return, life is good and Mojo's happy. This is one of the powerful things about the system. The fact that this composes correctly leads to a lot of really good things because it means that you can write natural code that a user would expect and it composes out the right way. In this ... the X is uninitialized. So you can have lifetime holes. This is actually quite important. What about this own convention? The own convention, when you say, I get ownership of an object, what you're saying to the compiler is, for the data flow stuff, entry to the function, it's a valid object. Of course, somebody just gave me a live object. But now, at the end of the function, I don't need it to be used. What that means is that within the body of the function, you can transfer it, you can consume it. If you don't use it, it gets destroyed. It gets early destroyed, which we'll talk about in a bit. What own means is it has a different behavior for the lifetime and the ownership of that object that you get passed in. I'll also say for completeness, the in-out self on inits are also magic. You have to initialize all the fields before the value becomes live. There's a little bit of magic that handles that. In-out is actually a lie in inits because it starts out uninitialized and it becomes initialized on exit. And so that's a little bit of a fib that we're using an overloading syntax, but that's different.
When you have move in it, do you have to explicitly transfer the ownership? Do you have to put the little hat?
Move in it takes self in out. This lie applies. I think this is beautiful because it composes the right way. When you define a move in it, the self is defined as in out, and just like any other init, and the other is defined as owned. So just like the bottom left, you have that thing that you're about to poach its body parts from. You can go and you can move its fields out. You can do horrible things to it. It's totally fine. And the destructor is completely correctly managed. If you poach one field out of it, but you leave another field, the fields you leave alone get destroyed. But the ones that you take are not. all completely correctly composes the way it should.
I just wanted to check if the implied assumption was true that would do things like check if there are potentially uncaught exceptions.
Yeah, absolutely. All the control flow nonsense that you could ever imagine. If you throw out of this function right here, you'll get an error if you don't initialize on the error path. But you could have if some complicated condition in the ... if some complicated condition, I'm about to throw X, here's your dummy value, and that's fine. You don't need sync, you don't need everything to funnel through a cleanup. As long as it's initialized on a path, it's fine. And similarly, try blocks have else's and they have except blocks, and so we need to track liveness, and we do track liveness correctly through all of these different things.
Is it true as well that if there's a field of self that you haven't initialized by the end of the init, that would be an error as well?
Exactly. The conceptual way that works is that you can think of a return from an init as being a use of self. It's just like any other use of self. This use of self, it's invalid right here because the first and second haven't been set up. But if you move it down here after the two initializations, it's fine.
I assume it would be invalid in between the two initializations, right?
100%. And you can go write lots of malicious test cases, please. As far as I know, everything's correct. So this is uninitialization and prevent you from blowing your foot off, but also make sure everything's initialized. There's also a dual to this, which is even more important, which is destructor insertion. Now that we know that everything's valid, you're not using a value that hasn't been initialized, we have to decide where to delete them. Simple example, I have string 1 and I use it. This is the last use of the string. I want to destroy it immediately. This is called ASAP destruction as soon as possible. Okay. What if I transfer it? I cannot delete it. If I delete it, bad things will happen because somebody else already deleted it, right? This is really, really bad. This problem of inserting destructors is also a widely studied problem. Mojo has, as far as I know, a fairly unique approach to this. I'm sure it's not literally unique, but it's very different, which is it destroys things early wherever it can. Coming back to exceptions, this is actually pretty complicated. You can write very natural code. A normal human would think, I have a string, it's initialized before it's used, that's fine. Here it's initialized before it's used, that's fine. Everything's cool, but where do I destroy these things? So now this is where languages really vary. If you look at a language like Rust or Swift, Rust actually has this thing called a drop flag. Rust will, in cases like this, insert a bool on the stack to dynamically determine if a value is initialized or not. And if the value is initialized, then you get an assignment, like operator equals. If the value is not initialized, you get a construction. Crazy to think that equals in Rust is context flow dynamic sensitive. That's not something that I think people really understand. That's definitely not true of C++. C++ is massively unsafe. That's a huge issue. Mojo takes a different perspective on this. So it has none of that dynamic behavior. It uses this as soon as possible destruction to say, using data flow analysis, determine when things can die, make them die as quickly as they can. It says, okay, you have stir and you have hello. I have a use of it, awesome. But there's no use of stir after this, right? It gets overwritten on all the paths. It ends up inserting a destructor inside the if, in this case, because it's known to be destroyed on either the if or the else path. This isn't an assignment. This is definitely an initialization. And so you get simple, predictable code. And after this last use, you get another deletion. This feature, I think, is really quite unusual. The way we explain the documentation is it's like an overly aggressive garbage collector, but done statically, but it brings a lot of power.
That insertion of the first del call, is it inside the block of the if?
Yeah, it's inside the block of the if, because if it were outside, you'd be deleting uninitialized data.
If that stir equals hello was done during initialization, so there wasn't a reassignment.
Technically, it would happen inside the else, the invisible else, and then it would happen after the use, because the else can have other code in it.
But it happened eagerly in both branches of the if.
Exactly. So why do we actually want ASAP destruction? The Mojo manual has a very good description of this in the death of value. The good thing about this is it eliminates tons of problems. You may not think about it. Tail calls are actually really important for certain functional algorithms. If you have an SV string on the stack, and then you have a tail call to yourself, the destructor for the SV string runs after the tail call. If you have an SV string on your stack and you call yourself in C++, you have no tail call, because the destructor runs after your tail call. So what looks like a tail call in source code is not a tail call. Simple, basic things that you'd expect as a functional programmer get destroyed by the C++ and Rust model. This also reduces memory usage. Deleting 4 bytes for a string, that's not a big deal. Why do we care about that? That's not going to reduce my high watermark. It turns out when you're in eager mode and you have a GPU tensor and you have 8 gigabytes of nonsense going on, freeing that thing aggressively is actually a pretty big deal. It also enables copy to move optimizations, which I'll talk about in a second. But also, more importantly, if you look at languages like Rust, Rust has a long series of problems that come out of the fact that its references end up living by default to the end of a scope. If you've used Rust, one of the very annoying, frustrating things about Rust is that many people argue with the borrow checker, and there's different forms of that. One of the major forms of that is that you have something that is a mutable reference that conflicts with other stuff, and it lasts longer than you expect. And depending on how long of a Rust programmer you've been, for a long time it used to be really, really, really bad. The Rust community is trying to incrementally pull this back with non-lexical lifetimes, a bunch of other stuff that they've been doing. They're doing all of this work to make lifetimes special and weird and trying to change their behavior. But really, if you make ASAP destruction happen for everything, then you solve that lifetime problem. Then you also get all the other benefits. Now, the one downside of doing ASAP destruction is that some C++ programmers would expect RAII. You expect to be able to have your smart pointer and then it gets destroyed at the end of the scope. There's an argument that Mojo should support that. If that argument is strong, we can add an attribute or something to change policy on this. But I think we should not, or we should default to not, because clearly, to me, ASAP destruction is the right default. If RAII is an important thing, it should be opt-in, not the default, first of all. Also, in Python, you have with statements. With statements are the way to represent scoped setup destroy things in Python. It's explicit, has a lot of advantages over RAII, which, if you think about it, is super weird. But I would argue that with statements are actually way better and more explicit and leads to more readable code. I suggest we resist the urge to fix that, even though we could.
There is an optimization here where if you assign a string literal to a string and the size is smaller than the current known allocation, and you don't have to reallocate, for example, would there be a reason to support something like that in Mojo?
We can always make simple things more complicated. The architecture supports stuff like that. We always could if there's a sufficiently motivating use case. We have a lot of other tools in our toolbox that we can do to solve certain kinds of problems. I would resist adding more complexity to the language unless we had to, but it's not a technical limitation. It's more of a design minimality trade-off. Let's find the use case and let's figure out the best way to solve for that use case, not jump to a thing because we know we can build it. One of the things I point out here is that this enables copy move optimizations, and we want the ability to optimize temporaries away. Let me give you a motivating example. Go back to our previous thing. It's silly to copy the string, right? I have a string, I have mutate, and I said, okay, if you transfer, then you don't get a copy. You just hand it off and life is good. Well, if you look at how this gets compiled, the type checker has to do this. It has to insert the copy because it doesn't know if name gets used later. It generates IR that looks like this, where you say, hey, I've got my name. Oh, by the way, the initialization looks like that in syntax, but like the initializer happens as an explicit statement. So when I'm passing this in, what I'm actually doing is I'm making a temporary on the stack. I'm copying name into the temp, and then I'm passing the owned temp into language, which, because it's owned, it then goes and consumes it and runs its destructor and it's gone. This is what the type checker does when you do this sad thing. This is, again, how this LValue to RValue conversion that I was talking about, that's what this does, is it creates a temporary, it inserts a copy. This only works if it's copyable, right? But now let's come back to ASAP destruction. Like ASAP destruction comes in and says, okay, cool, I've got this thing. This is the IR that I saw before. I'm going to go figure out where the last use of this value is. In this case, we're talking about name. It says, I see name gets used here. That's cool. I see name gets used here. I saw name got used in the loop. Where's the last place it got used? Oh, the last place it got used was its copying it. I will insert the destructor right after the copying it. That's correct. That's the right place to do things. It's nice that we're doing that. Wonderful. The cool thing about this, though, is that we're not C++. We're not some legacy language that has millions of lines of code. We can tell people that you have to define, copy, move, initializers, destructors that are value flavored. You're not doing RAII. You're not doing side effects. You use constructors for what they're designed to be. Now we can do simple optimizations because Mojo assumes that your constructors and destructors are well behaved, and it can know I'm deleting a thing right after a copy. When check lifetimes inserts a delete, if the thing's a copy, it all disappears. None of this copy, none of the temporary, none of this stuff ends up happening. It just gives you the same thing you would have got if you use the transfer operator directly.
Value semantics. If I use the value decorator for a struct, it will automatically create the move and the copy constructor, right? Do I ever have to worry about those, or there are cases where I have to build my own.
So you're saying, why would you want to define your own thing? The answer is if you're doing something that is not just a composition of the fields. If you have a struct with an int and a string and a float in it, that's cool. You'll just get the right thing because copying it, moving it is just copying each of the elements. But if you are implementing string and you have a pointer, your copy constructor needs to do a malloc. It's not copying the pointer, it's actually doing a more complicated semantic copy. And so that's when you define it yourself. And so what value does is it assumes you're a composition of simple other value semantic types.
What happens if language is not taking the argument as owned,
You never would have got this copy.
but it would have been still a transfer?
No, you never would have got this copy. And so you'd be passing name directly. So you'd get something that looks like this. The destructor would happen after the call to the initializer. Because this isn't destroying, if it's taken by borrow, it doesn't destroy it, it just uses it, then this would be the last use of name and the destructor happens after the initializer call.
What happens if I say return language name?
And it's borrowed. So then you are returning language by value. So it would initialize the language, it would then destroy name, and then it would return the language. That's why this copy happens, but it happens within the initializer of language.
So what you're describing here is an optimization, right? Where something that was originally semantically a copy becomes a move. What happens if you have a non-copyable but movable type? My current mental model is that in that case, you have to use the transfer operator to express semantically we're doing a transfer. Could you omit the transfer operator, or would you get a compiler error even if this optimization was possible?
You get a compiler.
Okay.
I'll talk about why the transfer operator has to exist on the next slide.
Regarding debug info, these immediate destructors, are we tracking somehow the lifetime for every variable?
Yes, we have 100% perfect liveness information about where they're constructed, where they're destructured, where they have holes. Absolutely.
What happens with sub-destruction when last use is under control flow at some iteration of a loop after the convergence point?
I would encourage you to go write examples and go look at the IR that gets generated. It's very cool. It's emergent behavior that happens with simple rules, which is the things that I like. Simple things to compose.
Is this name here, the consumes name, is that also a transfer implicitly as part of this optimization?
Yes, this ends up being a transfer.
Okay.
So this is saying I have a value and the thing consumes it. This is all pretty subtle, which is why I'm taking time to explain it. I think many Mojo programmers don't have to know this, which is awesome. What happens is they just get great behavior out of the box. Python programmers, for example, don't have to know anything about this because objects are just copyable. Like you don't have to worry about any of this stuff, but you don't have to write your std move. Like how many times have I written that damn std move, colon, colon, ah. This makes Mojo easier to teach because you just completely ignore transfer because nobody needs to know about it until you get to unmovable types. That I think is a massive benefit. This copy optimization thing should be 100% reliable. Let me know if there's a case that gets missed, but as far as I know, it is correct, it's reliable. The question then is, why do we need this transfer operator in the first place? Can we ditch it? This is about non-copyable types. If you're move only, you have to use this, which is pushing the complexity of std move into the use case of I have an advanced operation. Now, as an advanced programmer, I'm forced to know a new concept. This transfer operator is not something that everybody should be having to micromanage everywhere. So for example, the clients of the Max Graph APIs should never have to deal with this, in my opinion. That's not something we'd want a Python level programmer to ever have to know about. The flip side of this is that if you're a standard library person, if you're writing generic algorithms, your generic algorithm doesn't require copyability, which is a very important and useful thing to make things actually generic. That's where you do have to know about this. And so this is where if you're building an std vector someday, we don't want it to require copyability. And so using transfers explicitly, the compiler will tell you if you do the wrong thing. It will tell you if it generates a copy and you can't do that. It will not tell you if it generates a copy and then optimizes it out. That's one of the things that's a little bit subtle, but if you think about it from a UX perspective, I think this is a really important and good design point in the space for this whole thing. And also you contrast this to Rust, which makes you micromanage the heck out of everything. These are very simple rules that can be explained in an hour that compose out, and many Mojo programmers should never have to care about this stuff. So what I'll say is like Mojo is also smarty pants. This stuff is actually pretty cool. I'll give you one example of this is that it's field sensitive. Here I have a string pair with 2 strings in it. I can create a fully initialized string pair with everything going on, and I can consume 1 field. and that's fine. I can't use SP here, but I can use B. B is fully initialized. The Mojo compiler is fully field sensitive, and it will require that the field be initialized before it gets destroyed because it can't destroy a partially initialized thing. It can't run the destructor on SP, but it handles this. This is something where it's funny. The absence of this is, and the flakiness around this kind of feature set is where users get confused. So I'll write something that's obviously fine, and then they'll get forced into having to initialize things or not being able to transfer a field to something to avoid a copy, and getting the model right is a big investment up front, but it's really good.
Is there a requirement that if you partially move out of a type like that, that you have to reinitialize the field you moved out of before the destructor would be run?
Yes. And the reason is that it's going to run the destructor on string pair. So the destructor of string pair requires the whole object to be initialized. As the thingy on the right kind of glances at, there are advanced things, and so Mojo does have a mem-forget kind of equivalent thing if you're familiar with Rust, and there's other stuff going on, but users should not have to know about any of that kind of stuff. Let's come back to what's going on with this dangling pointer bug. Maybe some of y'all have been burned by this. Like, here I have a string, I get the data field out of it, either with a method or a field access, and I call process filed. This looks totally fine, right? No big deal. Is this actually correct? This seems magic. Let me tell you why this doesn't work. I'll be a compiler guy and lower this down. And so at the IR level, you get something that looks like this. You create your string on the stack, it's uninitialized. That fancy initializer syntax is actually just calling the initializer on the uninitialized value. That's fine. Then get the pointer out of the data, and I process the file. So this is what comes out of the type checker. What's wrong with this picture? Mojo is going to look at that, and it's going to say, this statement right here is the last use of stir. I get this totally unrelated unsafe pointer thingy back out. This is the last use of stir. Aha, I'll go delete stir. And so it goes and inserts the destructor there. And then of course you're very sad because this is a pointer into stir. The big problem that Mojo has, and the thing that has burnt many of you, is that Mojo doesn't know anything about what pointer is, what string is, what array is. It knows nothing about this. And so if you have an array ref, we don't want to privilege types. We want to enable abstractions. Mojo can't do the thing. It's simple brain. It's fancy in one way. It can't reason about this. This is a massive foot gun, as many of you may have experienced. And so how do we solve this? We solve it with provenance tracking. And so why don't I stop the slides here? And next time, I think that going through that and how this gets solved is actually pretty cool also, and is nifty.
Can I transfer explicitly, put the little hat thingy after str data and extract it from str and own it?
What will happen with the current string data is that you will try to transfer a pointer. Think of transferring char star. That will just copy the pointer. In fact, if you do that, Mojo will tell you, why are you doing this? This does not do what you want, and it will give you a warning saying, your transfer only makes sense if you have a borrowed value or if you have a L value. If you use transfer the wrong way, it tries very hard to tell you that you're doing the wrong thing. So it will say, that's not going to do what you want. Pointers, like classical pointers, just like char star, they don't carry ownership of the thing they point to. And that's the fundamental problem. And that's the fundamental thing that safe references have to fix.
This was just part 1 in the series. The next one will be on safe references in Mojo. That'll close the gap on all the lifetime features developers love and expect from Rust. The aim is to get that out in the next few months. So make sure to hit the like and subscribe button if you're interested in that. Join the friendly Discord community if anything didn't make sense, and we'll answer your questions. And you can try out Mojo now, the links are in the description. I hope you got as much out of this talk as I did when I first watched it. Thanks for watching.